lecture, we have discussed about comparison of longitudinal elasticity of a material with an ideal spring, and also thermal stress examples we have seen, etc. And we have discussed about stress and strain beyond elastic limit and beyond the proportionality limit, etc. So as I said, we are more or less done with the elasticity part. So we'll be coming to the second part of properties of matter, which will be to do with the properties of non-ideal fluids, that is surface tension and viscosity. But before that, just a couple of more things related to Hooke's law and elasticity. So another property of solid materials is called Poisson's ratio. So Poisson's ratio is to do with the fact that solid materials, when they undergo a longitudinal compression or extension, will also tend to undergo a change in cross-sectional area. And typically that expectedly happens in such a way that when there is an extension in length, there should be a reduction in the cross-sectional area and vice versa. Okay. So if this is, let's say, the natural length and natural area of cross-section of a solid material, so this is when they are, so these are the dimensions when not under any stress. But from this, when we take it to a situation where there is an elongation or there might be a compression, then what we expect in such a situation is that the elongation of length will result in the reduction of cross-sectional area, and the compression of length will result in an increase in cross-sectional area. So the property related to how much that happens, okay, by what factor we observe a change in length accompanied by a change in cross-sectional area. That factor is to do with the property of the material called the Poisson's ratio. So now if this area has become A minus delta A over here, or this area has increased to A plus delta A, then as I said, Poisson's ratio has to do with the relationship between the fractional change in area and the fractional change in length. Okay, so just note this down, we'll discuss the definition of Poisson's ratio. Okay, so what happens is that for Poisson's ratio, if we first define something called lateral strain, which will be actually like if this area corresponds to some radius like this. Okay, so here E minus delta A corresponds to pi into R minus delta R square. Okay, so lateral strain is basically delta R by R, which will become 1 by 2 times delta A by A. Okay. Or it can also be defined as delta D by D, where D is the diameter. Where A is the cross-sectional area. So this is how lateral strain is defined. And longitudinal strain, as you know, defined as delta L by L. The fractional change in length. So Poisson's ratio is defined as generally denoted with the symbol sigma. It is the lateral strain with respect to the longitudinal strain. But also here when we define lateral strain and longitudinal strain in these formulae, the strains are defined with algebraic sign. So delta L by L will be positive for an extension and negative for a compression. So in that case, this is defined as negative of the lateral strain divided by the longitudinal strain. So there is an interesting property related to this, which is why I'm coming to this. So for most materials, one would imagine that Poisson's ratio is a positive quantity, because if the length compresses, then the diameter should increase. Whereas if the length extends, then the diameter should decrease. So negative of the ratio of these strains should come out to be a positive quantity. However, there are interesting materials known for which Poisson's ratio happens to be a negative quantity, which means that when the length elongates, the diameter also increases. So this is the typical case like for a metallic cylinder. Or rod. It will typically behave in this way, that is Poisson's ratio is a positive quantity because the behavior of the two strains is opposite. One being positive will result in the other being negative and vice versa. Okay, so as I was telling you that typical real life materials, naturally occurring materials like metals, etc., have Poisson's ratio positive. But both artificial and naturally occurring materials are known which have negative Poisson's ratio. For example, artificial materials like, for example, Kevlar, which is used for making bulletproof vests, etc., or naturally occurring materials, like some examples of some porous rocks. These tend to have negative Poisson's ratio. So what negative Poisson's ratio means that the ratio of transverse or lateral strain is to longitudinal strain is negative. Okay. Sorry, that ratio is positive because this quantity is negative, okay, because sigma is negative. So which means that negative value of Poisson's ratio, it implies that if length is elongated, the diameter or correspondingly the area of cross section also increases. Okay. Or if length is compressed, the diameter is also compressed. So you might wonder how this can happen. So this is very interesting. At the molecular level for such materials, what is happening is that the molecules are sort of having intermolecular bonds which act like hinged materials like this. Imagine you have made a structure with some materials which are hinged together like this, rod-like materials which are hinged together like this. Now the two horizontal rods are made of elastic material. So when you tend to pull such a material, what will happen is that okay, so when you tend to pull it, what will happen is that we tend to increase in diameter as well as increase in length. So applied force like this. Or when you push it in, this is what tends to happen, that because of the longitudinal elasticity of these horizontal bars, this tends to compress, but because also they are attached to other parts through hinged kind of structures, so this dimension also decreases. So this is like an imagined artificial structure made of rods which are hinged together. But what happens for materials which are doing this at the molecular level is that the intermolecular bonds and the way the molecules are arranged with respect to each other, they at the molecular level create these kind of microstructures which have this behavior that compression of length results in compression of the transverse dimension also, and elongation of length also results in elongation of the transverse dimension. So this is just a factual thing you should know, like nothing related to this in your numerical analysis. Kevin, I'm not sure actually what the whole chemical formula of Kevlar is, but I know that it is, so any material that is that has the capacity to absorb mechanical energy during collisions, absorb high amount of mechanical energy very efficiently, and also absorb momentum or impulse very effectively during collisions. Those type of materials are typically materials which have negative Poisson's ratio, and they are useful for making impact absorption structures. Okay, so now let's also look at an example or two of application of shearing. For example, suppose we have a rough surface with a coefficient of friction of 0.6. And on this, we have kept a rubber block like this. Now, this dimension let us say 1 meter, and the density of rubber is 0.8 gram per cc. Now what we are doing is we are applying a force tangentially at the top. Some external force is applied tangentially at the top. So you have to find, first of all, the maximum force such that it does not slip, and given that the modulus of rigidity for rubber is so much, we have to find the shearing strain for this maximum force. So notice there's one piece of data missing over here, which is the cross-sectional area, but then density of rubber is given to you, so you can make use of that. Okay, I'll scroll back up. We'll come back to this question. Yeah, that's correct, Naman. Okay, anybody else got the answer other than Naman? So you can understand that the first of all, from this data, we can get the cross-sectional area. This area is A. We get the cross-sectional area as the volume divided by the length, right? And the volume we will get as so this is the cross-sectional area. Mechanics wise, you can understand the first part's answer. The maximum force so that it does not stop, does not slip, is equal to the limiting friction. So mu was given to us as 0.6. So this will become 30 newtons. So now for this external force being equal to 30 newtons, the shearing stress tangential force divided by area of cross section. So what will happen is when we apply this force, this would have got bent through an angle theta because of this external force and friction in reaction acting like this. So this is creating shearing in this material. So this tangential force is nothing but this external force of 30 newtons. So this is the shearing stress. And from this now we'll get the shearing strain. This will become 6 into 4 by 5. So 24 by 5 or 4.8. So this angle by which it bends or the shearing strain is okay. So modulus of rigidity is any strain is a dimensionless quantity, as you know. Okay, people, so hope this example was clear. Now there can also be situations in which a material is undergoing both shearing as well as tensile stress and strain. Okay, so let's look at a quick example of something like that. So we have a metallic bar like this, which is rigidly attached to some surface like this, like a wall. So this is a metal bar which has Young's modulus Y, modulus of rigidity eta, natural length L, and area of cross section E. Now to this same one, if we attach some mass by hanging it vertically from the far end of the metallic bar, then what we will see is that the metallic bar will tend to bend. Instead of this being what would have been its natural shape, tend to bend a little bit like this. So I'm drawing an exaggerated diagram for the bend, but bends through an angle theta under the action of some weight. So if the metallic bar itself is negligible in mass, compared to M. So now we can see that suppose this angle is beta. So here this angle will be more or less beta, be slightly less because of the bending. Okay. So the tension in this wire would have created both longitudinal as well as transverse components. This would have created a component of force is normal. So this angle was beta. And the tangential component of force at the surface. So now what we'll see is not only this is bent, but this is also elongated, become L plus delta L. So we will see that normal component of force per unit cross-sectional area is tensile stress. So tensile stress upon tensile strain is equal to Young's modulus. So delta L will become mg cos beta upon Ay L. And tangential force per unit area divided by tangential strain is equal to modulus of rigidity. So the shearing strain or the angle by which it bends, that would have become mg sin beta divided by eta into area of cross section. So the same material is undergoing both shearing. So the bar is elongated and sheared at the same time. This is the amount of elongation. And this is the shearing strain or the angle by which it is bent. Okay, Snigita, this one, that rubber block one.
Yes, sir.
Yeah. So this angle that we get over here, by which it bends, this angle, remember, is in radians. Okay. It's not in degrees, it's in radians, because it's the ratio of that x by L tan theta kind of thing actually.
Done, sir.
Okay. This next question is clear, I hope.
So 1 minute.
Yeah. Okay, so this is done, people. All right, let's move on to an example of volumetric stress and strain and bulk's modulus. So first we will see volumetric stress and strain in a solid material, but then we'll also move on to bulk's modulus of ideal gases, okay, in thermodynamic processes. Like you've heard of the term adiabatic bulk's modulus or isothermal bulk's modulus. You'll understand how to calculate those things and how they work. But before that, as I said, let's look at an example of application of this in the case of a solid material. Let's say we have a water tank. Density of water is standard value 1 gram per cc. Now we have a spherical rubber ball. So a solid spherical rubber ball. So the bulk's modulus of elasticity for rubber, that is given to us as okay. So when the ball is placed underwater, so let's say it's placed somewhere here, and we'll assume that in this case the rubber is having more density than water. It's one of those high density rubbers in comparison. It's not going to be floating, it's sunk. So it's underwater at a depth of 15 meters. Calculate the volume stress on it, the volume strain experienced by it, and from that we want to calculate the percentage change in the radius or diameter. Percentage change in radius and diameter of the rubber ball as a result of this volumetric stress and strain. Just work this out quickly. Just use the definition of or the statement of Hooke's law for volumetric stress and strain. That ratio of volumetric stress to volumetric strain. Modulus of that ratio is Bulk's modulus of elasticity. So obviously, when the volumetric stress is positive, that is there is excess pressure, the volumetric strain is a negative quantity because the volume will compress. But the ratio, the magnitude of the ratios, that is equal to the Bulk's modulus. Okay, so people, yeah, Aman, I will just confirm your answers. Okay. So first thing we'll do here is we'll understand that this is at natural atmospheric pressure. Okay. This is the natural state. Okay. So let's say the radius is r, so the volume is pi r square. But when over here the pressure is P naught plus delta P, where delta P is rho gh, where h is this depth. So this is your volumetric stress. Okay. And as a result of that, the radius would have decreased. Okay. Let's say R naught minus delta R. So the volume also would have decreased. Four by three. What am I writing? Pi R cube. Like this. Okay. So what we can understand is that volumetric stress is 1000 gram per cc into, let's take 10 meters per second square into the depth which is given to us as 15 meters. So it is 1.5 into 10 raised power 4, sorry, 10 raised power 5 pascals. Is 1.5 atmospheres in fact. So the volumetric strain, which is this we have to calculate. Now, ratio of volume stress to volume strain. This is equal to bulk's modulus. So the volumetric strain will be negative over here and it will be equal to this divided by so this is our volume strain. Okay, so Aman, hope you have seen the correction. I think there was some miscalculation of power. Naman, your answer is correct, but this is now a B part. This was the A part, volume stress. This is our volume strain. Now, for the percentage change in radius, volume is 4 by 3 pi r cube. So PV by V is 3 times dr by r, or we can say delta V by V is approximately 3 times delta r by r for small changes, for small fractional change. propagation of error concept, we can use that. So delta R by R be 1/3 of delta V by V. So that is minus 2.5 into 10 raised to minus 3. So the percentage change will be minus of 0.25%. So this is the C parts answer. So, you can say either we have used calculus or let's say we've used just the error propagation concept, which also comes actually from calculus only, or binomial approximation, or whatever method you choose to prove it. But if one quantity is proportional to another quantity to the power n, then the percentage of fractional change becomes n times, provided the percentage of fractional change is a small one. This type of question becomes important. Another thing you can be asked over here is the percentage change in density. So if the volume reduces by 0.75%, then the density will increase by 0.75% because volume and density are inversely proportional. So that's another thing you can add to the question here. Add a fourth part, that what is the percentage change in density? So that will be density is inversely proportional to volume. So it will be negative of percentage change in volume. So it will be plus 0.75%. Okay. So additionally, also see that okay, so this all being examples of application of volumetric stress and strain and bulk modulus concept. Now we come to volumetric stress and strain and bulk modulus for an ideal gas undergoing a thermodynamics process. So bulk modulus is defined in a sort of instantaneous manner over there. It is defined as dP minus of dP divided by dV by V. So what happens is that when an ideal gas at a state of PV, okay, is undergoing a compression, let's say. So this is a differential change. So at that moment, for this differential change, the volume stress at that moment is the change in pressure, and the volume strain is minus dV by V. Or same way, if it is going through an expansion, so the pressure would decrease by a differential amount, the volume would increase by a differential amount. So in this case, the volume stress will be a negative change in pressure. The instantaneous volume strain would be a positive fractional change in volume. But either way, we would define the bulk modulus as so this is the formula for bulk modulus. So what you understand is that during a process, bulk modulus has an instantaneous value. At an instantaneous state. And this also depends on the path, that is the type of process. So for example, obviously for an isobaric process, the bulk modulus is 0 because there is no change in pressure. And for an isoporic process, bulk modulus is undefined because change in volume is Okay, so now based on this, we develop a general formula for polytropic processes, which, as you know, is a family of processes. So it covers all the standard processes also. So bulk's modulus for a general polytropic process. So PV to the power alpha is constant. So if we differentiate this, we'll get small change in this should be 0. So differentiation of first term into second plus first into differentiation of second should be equal to 0. So we take V to the power alpha minus 1 common in these two terms. You can see that we'll get V dB plus alpha P dV equal to 0. So obviously volume is not 0. So V dP plus alpha P dV must be the term which is 0, which basically means that dP into V is minus alpha P dV, or minus of dP divided by dV by V is equal to alpha P. So that means the instantaneous bulk's modulus is the instantaneous pressure multiplied by the polytropic exponent alpha. So for example, for an adiabatic process, alpha is equal to gamma, which is Cp by Cv. So the value of bulk's modulus at a point is nothing but gamma. So for example, let's say oxygen gas at a pressure of 2 atmosphere is undergoing an isothermal expansion or an adiabatic expansion. So find the bulk's modulus for each. So you can see the answer to that becomes so bulk's modulus is instantaneous pressure. So therefore, approximately at this moment, okay. But the second one, bulk's modulus is gamma P. At that particular instant. Okay. So in general, this is how we calculate the bulk's modulus of elasticity for a given gas at a given state undergoing a particular type of process. As you can see, it depends on the pressure. Out of the state variables, it depends on the pressure. And out of the path variables, it depends on if it's undergoing a general polytropic process. The path variable there is alpha, the exponent term. Okay, so people, with this we come to a conclusion of the elasticity section. Yeah, sorry, I had thing got disconnected in between, but continuing now. All right, so with this we complete the elasticity portion of properties of materials. Now we will move on to the properties of non-ideal fluids, which is viscosity and surface tension. So we'll start with the property called surface tension. So surface tension is a very interesting property which has to do with the elastic nature or the elasticity of the surface of a fluid. So this is a material property for liquids associated with the elasticity of their surfaces. So first of all, let's start by defining what is the surface of a liquid. So surface of a liquid is defined as a thin layer of liquid molecules, or you can visualize it like a film, thin film of liquid molecules that separates the body of the liquid from its surrounding environment. But by thin, what we mean that the thickness of this layer is of the order of magnitude of few times the molecular diameter. So we're talking about an extremely thin layer. So an example would be, suppose we have a cylindrical vessel with liquid inside it, open cylindrical vessel with liquid inside it. So there will be a thin layer of molecules right at the top, which separates the surrounding environment, which is air, and the volume of the liquid. So the surrounding environment being air, and this being the body or the volume of liquid. Let's say it's water. Then this thin layer over here, this is the surface that we're talking about. Or another example would be, suppose we have a volume of fluid in a zero gravity environment. Now, due to very interesting factors, we will discuss later, that such a volume of liquid would actually take a spherical shape because it's in zero gravity environment. So it would be in the shape of a solid sphere of liquid. Now the surface that is which separates the volume of the liquid from the environment in this case, which would be the vacuum of space. Or if it's inside a spaceship, then it would have artificially oxygenated environment. But either way, the lack of gravity would make the volume of such a liquid naturally take a spherical shape. So the thin layer which separates the volume of liquid inside the solid sphere with the outer environment, that would be the surface. So that is the definition of a surface. Now, why a surface has elasticity? We'll discuss that next. Again, it has to do with the nature of intermolecular bonds and intermolecular forces, which in this case are called the adhesive forces. Cohesive and adhesive, two types of forces. Yes. Okay, so now why the surface acts differently and has elastic property compared to the body of a liquid? Let's understand that. Okay. So the elastic nature of the surface, it comes from the cohesive forces. So a liquid surface actually acts like an elastic membrane. You can see a lot of evidence of this from physical properties. Okay. For example, we will be studying waves in the next section of physics, but we will see that transverse mechanical waves are able to propagate on a liquid surface okay, because of its elasticity, because of its elastic nature, which we will see very soon is defined by, or it's quantified by its surface tension. So these type of waves that you see on a fluid surface that propagate, where the fluid molecules are actually oscillating up and down, okay, but the wave is propagating in the tangential direction. That happens only because the surface has the property of elasticity. Had it been an inelastic kind of material, then waves, transverse waves, could not have propagated like this. Okay. Then another example, you will see that okay, certain insects are able to literally walk on fluid surfaces. Okay. They're not floating. Okay. No part of their body is submerged. So that is because the elasticity of the surface is able to support their weight. Another example of this kind of a situation is you can try this at home. It's possible to balance a thin needle, a thin steel needle on the surface of typically water. It will be very difficult, but if you mix some soap or soap solution with the water, just a moment, I'll refile. Yeah. So if you try this experiment at home with using some kind of soap solution or liquid detergent mixed with water, you'll be able to do this. It's possible to balance a thin steel needle on the surface of soap solution or detergent mixed in water. So even though you know that the density of the steel is much greater than the density of water or the density of the solution, so there's no chance that it is actually floating. Okay, but at the same time on the surface, okay, so you can observe that if this is the surface of a water body on which you have put very gently, you placed a metallic needle like that. So you'll see that where the needle balances, the surface is slightly indented. So it's like a membrane that has got indented from the weight, okay, and that's what's balancing it. But if you place the needle inside the liquid, there's no way the buoyancy is maximized because the entire volume is submerged, but no way the buoyancy will be able to balance its weight. So again, there is evidence that there is some additional type of elastic force that the surface is able to apply when it gets indented because of the weight of the material, like the thin needle, like in this case, or an insect trying to walk on the surface in the above case. So the moment the weight of a small mass creates some kind of a indentation or some kind of a deformity in that thin layer of molecules which we call the surface, it's able to apply a restorative elastic force. So that again is evidence of the fact that such a material has an elastic property or is capable of applying elastic forces, and hence the need to define its property as surface tension. Okay, so now let's understand the origin of this elasticity. As I told you, it comes from the nature of the cohesive forces. So if you look at the situation in terms of cohesive force is the intermolecular attractive force between like molecules. So in this case, if it's like say like a water body, then the intermolecular attraction forces between water molecules, they are called cohesive forces. So they are the intermolecular attractive forces between like molecules, that is between the molecules of the same species. Okay. So now if you visualize a water molecule at the surface, it is experiencing cohesive forces in this sort of direction. Whereas if you visualize a water molecule inside, it is inside the body of the liquid, it's experiencing cohesive forces in all directions. So this difference, this creates the property of surface tension. So now basically what happens is if this water surface, if because of some external force or something, it's made to indent like this, then automatically the forces which are acting like this, they will tend to grow stronger. And as a result, there will be a restorative force in this sort of direction, which is generated. So that creates the elasticity. So hence, basically, that diagram I showed you earlier, where on a surface of liquid, we had placed a thin needle. So this is a thin metallic needle on a surface. Then where the needle is placed, the surface will just have a bit of an bump kind of thing in it. So if you draw a very magnified diagram of the cross section of the needle, so this is magnified cross section. So what has happened is, because of the weight of the needle, the surface over there, or the layer of molecules at the surface, it got slightly bent like this. So they are on each other, they are applying cohesive forces which are like this, which is generating an upward force on the needle, which is able to balance its weight. That's how the needle is able to balance and be in equilibrium on the surface. So these are surface tension. It is a property that is observed due to the nature of cohesive forces acting tangentially at a surface. That is the origin of this property of surface tension. It's always to do with intermolecular interaction, whatever type of material property we see, whether it is elasticity or restorative forces due to external stress and strain, or we are observing in this case the elasticity of a surface in the form of surface tension. It's always got to do with the nature of the intermolecular interactions. In this case, we see that the molecules at a surface behave somewhat different compared to the molecules inside the volume of the liquid. And that behavior gives the surface that sort of elastic property, that it almost behaves like a stretched rubber membrane, that if you put pressure on it from above, it will tend to deform, but it will also tend to apply a restorative force. It has that flexibility and that elasticity about it. So that at a molecular level is because of the nature of how these cohesive forces line up tangentially at the surface. So the surface bends slightly, that tangential force, it acts in such a way that it contributes to a restorative force. Okay, so this is just a basic introduction to surface tension. We will conclude here today. Next lecture, we will look at the mathematical model of surface tension and the definition in terms of surface tension as a material property. We'll see that it has dimension of force per unit length or energy per unit area. and we'll take it from there. Okay. So in the meantime, try to finish all questions to do with elasticity, right? And as I've told you before, for thermal stress problems, you will have to go back to the thermodynamics section of H.C. Verma. That heat and temperature chapter. Towards the end, it has few questions to do with thermal stress, and also for bulks modulus for gases undergoing, various thermodynamic processes. Those type of questions you won't find too many in HC Verma, but some in the module, which are to do with adiabatic or isothermal or general polytropic bulks modulus. So that is something additional to the elasticity chapter that you can do. Apart from that, the important things in this chapter of stress and strain and Hooke's law application was to do with the situation where there is non-uniform stress and strain and one has to use integration. And of course, combination of materials where we use the equivalent spring constant method. Okay. So it's pretty straightforward once you know those techniques of solving the problems. So make sure you're familiar with all that. So that's it for today's class. Thanks, people, and wish you all the best.
Thank you, sir.
Okay, people, bye.